Hi, everyone, and welcome to the session on µTVM. So just to quick introduce ourselves, my name is Tom Gall. I'm one of the members of the AI team, and with me is Gustavo. Gustavo, you want to do a quick intro?
Hi, I work with Tom with TVM µTVM Project. Thanks for attending us.
All right, so let's get going. So if you would, go ahead and advance the slides, Gustavo, to...
Yeah.
So what we're going to do is we're going to start out and we're going to talk about what is the TVM project in general. And then as we kind of go through the succeeding slides, we'll get into talking about µTVM in particular, which is about TVM for microcontrollers. So in general, the TVM is a machine learning framework, and it's an agnostic compiler stack. So it has the ability to target CPUs, GPUs, NPUs, all sorts of different kinds of offload, as well as do some amount of heterogeneous capabilities between those types of devices. Some of the key things that's really important about the particular project is it's an Apache project, which means it has all of the Apache style process around it, including governance, most importantly. It is under an Apache version 2 license, so it is open source, by one of the strictest definitions of what open source is. You can go to tvm.apache.org. Those will bring up a number of informational pages about the project, everything from documentation to how to get the source code to the yearly conference that we have. And so one of the things that we find most exciting about the TVM project in general is it supports a wide range of hardware. So this includes, hardware from the very, very large to the very, very small. And so as a result of that, we've been putting time and effort into it, and we think it is an important part of the ARM ecosystem. Go ahead, Gustavo, next slide. So let's talk a little bit about, what is the TVM architecture and what does it kind of look like? So at the very upper left-hand corner, what TVM has the ability is to consume models from a variety of different machine language frameworks. So this is, your PyTorches, your TensorFlows, Keras, MXNet, a whole wide variety of frameworks. And then as it consumes those models, it will go and transform it into a number of different IRs that are available to it. So, the route into these ARs is really all about, taking what will be the internal opcodes from a framework such as TensorFlow and then transforming into something that would be, more closer to what will be optimizable for the compiler stack. So then as we lower ourselves, we will go and look across the optimization space for how can we combine opcodes, how can we rearrange nodes, how can we potentially trim nodes from the framework and end up with a more optimized experience. And then so as you, of course, get to the lowest level of the slide, you'll see that we will then get to a point where we need to now target real hardware. So via LLVM, we may be targeting an ARM CPU, such as an ARM64FX. We may be targeting a GPU, an FPGA, or what have you. And then on the very right-hand side is something which is a very important piece of TVM, where it has a concept called auto TVM, where it can take feedback with each succeeding step and end up with a higher performing model, where by trying different paths, it can see, oh, okay, well, if I arrange the nodes in this particular way, I get 5% better. So I'll choose that path. And it's through the magic of auto TVM that we are able to do this feedback, use this feedback to then end up with a better performing model. Next slide, please. So that's all great, fine, and dandy. We've talked about things when it comes to ARM hardware and Cortex-A devices, but let's talk about Cortex Class M devices. And so that's the world of microcontrollers. And of course, here we have an ST Discovery board. So this is the 746, which µTVM actually runs on today. So next slide. So this will be the last slide that I talk about before I hand things over to Gustavo. And so what I really want to kind of get into is, when it comes to microcontrollers, and you can do inferencing on a microcontroller, how do you do that? What are some of the issues that we're trying to wrestle with as we're implementing µTVM? So one of which is we need to be able to ingest models from a wide array of AI frameworks, just like TVM does today. So you ought to be able to import a TensorFlow Lite model. You ought to be able to work with a PyTorch model, so on and so forth. The problem, though, is when you have all these different kinds of models and frameworks, you end up with a Cartesian product of models, frameworks, and hardware that you ultimately need to target. And I would even add in there, you have also a set of real-time operating systems that you might want to be running on your microcontroller at the same time that you're doing inferencing. So that said, we also, when it comes to optimizations for running a model on a microcontroller, have a wider variety of characteristics that we need to be tuning for. It's not just make the model run faster, but we also have to be thinking in terms of the working set size, i.e. how much memory are you fitting into, as well as power consumption. When you're in a world of pen-like batteries and such, you need to be thinking about these things. Then likewise, offload is very important in this world as well. So we're not talking about just doing things on a CPU, although certainly in the microcontroller world, you may only have a CPU there. You may not have an NPU. You may not have a DSP. So these are things that the framework, and µTVM in particular, needs to be able to handle gracefully. Also, in the case of microcontrollers, another way of making a model smaller and being able to fit into better working set size is quantization. So this is when you're working with 8-bit data types or 4-bit data types or even something smaller than that. And so through pruning and distillation, we need to retain a reasonable set of accuracy. So all of this kind of said, you have a really interesting set of issues which are really unique to the microcontroller world that µTVM in particular needs to be able to handle. And lastly, and probably most importantly, is you need to be able to deploy at scale across a family of devices as opposed to just one particular device with one particular type of microcontroller on it. And so as a result, we want tools to be able to handle this too. So let's move ahead to the next slide, and I'll turn things over to Gustavo.
One of the nice things about TVM, as Tom mentioned, is that TVM can target microcontrollers, and for that specific runtime, there is a minimal runtime which leverages the TVM framework and which implements an RPC server, and also is able to run on top of a Zephyr or any other RTOS, and also RTOS-less without any RTOS under it. And it's written in C and C++, and has got lots of Python bindings. So the user can use Python APIs to generate final firmware images ready to be flashed and get µTVM running on the targets. And µTVM is a work in progress, so it has been lots of work recently and currently on that front. The typical development workflow on TVM and also on µTVM is that it takes as a input any various formats is exported by AI frameworks like PyTorch, TensorFlow Lite format. And it loads it into a Python object, and then TVM parses it and generates a intermediate representation. And then it uses a LLVM API internally to convert, given a target, to that intermediate representation, which is called relay IR in TVM, to a final to C sources, for instance. And then once we've got the C sources, one can use any normal to chain for a target to compile finally the C source generated by TVM into a native code to run on the board. So we've been working since the beginning of this year with a couple of targets, ARM targets, and experimenting and µTVM on top of those targets using primarily Zephyr RTOS. And from a Zephyr's perspective, the µTVM is just an application for Zephyr. And in doing that, we have successfully run µTVM on Nucleo boards, which has a Cortex-M 7 based MCU. And also we successfully run µTVM on Disco board, which has got this very same MCU as the Nucleo board, but with some additional peripherals and the LCD. So the memory map memory layout is a little bit different. And most recently, we were able to successfully run µTVM on the MPS2 AN521 board, which is picture number 3. And this is a quite interesting board because this is actually a FPGA board. And one can download a standard FPGA image from ARM and flash into that board. And it will provide exactly the same specification found in AN521 application node. The AN stands for application node, and it specifies all the memory regions in devices that follow that specification. We have patches. Some patches go to Zephyr, and other patches go to µTVM itself to enable µTVM run on that MPS2 board. And looking ahead, we are looking at the MPS3 EN547 board, which has a Cortex-M55 based MCU, and that board is quite interesting because it has got a Ethos U55 NPU, and so we can offload offload some operations to be executed. And delegate that to be executed in the NPU, not on the MCU. Some of the there are current work from the embedded folks at Linaro to enable Zephyr run on the MPS3. There was a pull request for that, but we couldn't. We don't have support on QEMU. However, there is the FVP from ARM, which is a fixed VFP. I'm sorry, virtual fixed platform, which is the emulator from ARM, which one can use instead of QEMU to run and experiment µTVM on top of MPS3 boards. So another thing which is interesting is that TVM comes with a tool called the TVMC, which is a command line interface tool. And it has two main use cases. One of the first use cases to use development workflow. So it allows one to split the compile and run, for instance, or debugging stages on µTVM using TVMC without having, for instance, to run through all the stages of the workflow at once. So you can for instance, just run the model and start debugging it instead of having to compile a model and flash it and run it all over again, as if one would do using the Python APIs. And the other use case is that µTVMC can generate just the C sources, for instance, and it can be readily be picked up by another project and be used inside of make files, for instance. So this is the main two use cases for µTVMC. However, currently µTVMC only doesn't support µTVM target. So we have proposed an RFC to add that support for micro and microcontroller units on TVMC. On doing that, we did realize that some refactor was necessary to accommodate the changes necessary to enable the µTVM targets on TVMC. And so the community proposed two new RFCs, which is the model library format in the API project, and the project API RFC. The idea is that the flow stages that generate artifacts like syssources or compiled objects will use the model library format to store the artifacts. And on the other hand, the project API will allow better integration with various RTOSes, not just Zephyr, because currently Zephyr is kind of too tight coupled to the µTVM code. And in doing that, we are proposing in that RFC a new context called micro, which will support the workflow for micro TVM targets. And the lines in blue are just an example of workflow, a typical workflow that one will follow when using TVMC with micro TVM targets. And so we are proposing, like, for instance, a micro create project where you can specify Zephyr backend or embed backend and so on. We are proposing a micro build, which will command, which will get the source and generate the firmware. And we are also proposing a micro flash, which will effectively flash the generated firmware into the target board. And finally, micro run, because the run for micro targets has some specific steps like open connection with serial ports and so on. So this is I just would like to mention three main components about the firmware, which is flashed which is generated by TVMC and which will be flashed into the device. And it has three main components, which is the first one is the code that is necessary to initialize all the device and peripherals, and it has code for the libraries to access time control and vendor code specific for performant operations, which will be related to the model. The second thing about the runtime, the µTVM runtime, is that it is MISRA C compliant, which and it has a RPC server, as I mentioned before, to allow interaction with the host, so host can command which operations are necessary to be executed at the target site to run the graph or to run the model and grab result and get the final result from the execution of the model in the target. And that runtime also has ability to have sessions, and each session is open to when the host establishes connection with the RPC server to request an execution of an operation. And finally, the third part of the binary contains the compile TVM operations, the node from the graph of the model, which is generated specifically by each model. And also, there are some interesting things that we can do with the operations, like determine at compile time where the operation code will land in the target device. And this is important because depending on the board, the RAM memory is not is mapped to different devices, and some of the devices might be quite slow. So we can change that and put the operation code in a faster run for execution. So for anybody interested in looking at µTVM, I recommend looking at that script, which is an example of how to load compile and run a model, a TensorFlow-like model for predicting a scene function. And it is found in the repo in tutorials /micro/micro_tflite.py. And the thing I would like to I just would like to walk through the main parts of that script, which is precisely the workflow we have discussed in the previous slide, which is the first we load the TF file, and we have the Python model object, and then we convert it to a relay IR and the weights, and then we specify a target, a board, and then we request TVM to generate the sources for that relay IR, and it uses a LVM API for that. And then the result is that we, after specifying the target and compiling the IR, we have three main outputs, which is the JSON file with the which represents the execution of the model we have compiled, the syssource with the operations, and the model parameters for each layer of the model. So after that, we have everything to call like Zephyr, the Zephyr backend, and specify a compiler for that. And in that case, we are basically using Zephyr's SDK toolchain to convert the final C sources generated from IR to native code. And once we do that, we have a firmware ready to be flashed. We open a session. And when you open a session, the µTVM libraries will just flash the firmware and open a session. And we define the input, like in that case, it's an angle for the model, and we run it, and we grab the result of the execution. So that's what I had to talk some quick introduction update about µTVM, and in the following slides are quite interesting and helpful information about the roadmaps for TVM and µTVM, and also we have Tom is the coordinator of the project, and we have a Slack channel, so feel free to join us and ask more about TVM and µTVM. That's it from my side. Tom, do you have any additional comments?
No, I think given we have about 2 minutes left in the session, let's pause for questions. So does anyone have any questions?
Objections or suggestions, or like don't do that, guys, or whatever.
Well, we'll certainly be around through all of Connect, and be happy to entertain any questions if they come to you later, or send us an email. We're always happy to chat. Oh, there we go. So we have one question is, do TVM and µTVM build from one code base, or is it semi-detached project? They are all in the same Git tree. So essentially it is one code base.
Yeah.
Okay, any other questions? If not, I think we probably can go ahead and end the session. All right, well, thanks everyone for being here today. We appreciate having this opportunity to present to you on µTVM.